Assalamualaikum warahmatullahi wabarakatuh. Okay, this is our first time to have this non-face-to-face class. Okay, right. So last week we did cover on the AC voltage controllers, whereby we look at the single-phase AC voltage controller, why we need them, and the application of these AC voltage controllers. We look into the circuit topology, whereby for EPO510 we only covers the inverse parallel connections, whereby you have two thyristors and two type of control technique, namely the phase control and also the integral cycle control. Okay, for a phase control, we look at the we analyze the circuit with a purely resistive load, and then we proceed with the R plus L, the normal R plus L load conditions. And apart from that, we also have to address, the issues of the power that being delivered by the circuits, which consists of AC waveform. Yeah? Okay, so normally, conventionally, in the system of in the normal system, we have a sinusoidal supply voltage and we have a sinusoidal supply current. Therefore, the average power calculations is actually given by P equals to the RMS of the voltage supply multiplied by RMS of the supply current multiplied by the cos theta, which is the angle between the voltage and the current. And in power electronics, normally we have a non-sinusoidal current, input current. For example, if you talk about the full wave rectifier, we sometimes have a square waveform, and we also did look at the three-phase 6-pass rectifier, where the current is quasi square waveforms. Okay, and also when we talk about the AC voltage controllers, we might have in the future, or we might have a voltage supply voltage which is not sinusoidal, a non-sinusoidal supply voltage, and the current is, for example, we have a square waveform current. So how can we calculate the actual power from it? Okay, so in practical, if you are engineer later on, you're going to have this measurement meter, a power measurement meter, whereby on top of that it shows that there is a true power meter. So what is that true power meter? So today we're going to look at how to calculate in the case of we have a non-sinusoidal voltage supply and of course a non-sinusoidal current supply. So for example, in this simulation, we have the supply voltage consists of fundamental components, the third and the fifth harmonics. That can be shown from the waveforms here. And then we have a square waveform that we've discussed before, whereby for a square waveform we have a fundamental and all the odd harmonics components. Okay, so how can we calculate the power, the average power from this kind of waveform? Okay, before we proceed, let's look at the definition of Fourier analysis, where we know that for every waveforms, any waveforms can be represented by an equation of A0 over 2, which is the average term of the waveforms, and then Cn sine n omega t plus phi n. So whereby phi n is the inverse tangent an over bn, and Cn is the square root of an squared plus bn squared. And we also know that an, the equation for an is 2 over t and the rest, and bn is 2 over t and sine omega t. So any waveform can be represented by this waveform. Okay, to solve this power equation, we're going to use the note from Ericsson, which is also the well-known lecturer, the well-known person in power electronics. he did produce this notes on the average power, but for Mr. Erickson's write an equations with the voltage and current, okay, for this circuit, for this simple equivalent circuit whereby we have source and load, and the voltage is between this source, and then we have the current that flow into the load. So both voltage and current here can be represented by this periodic Fourier series equation, whereby V0 is the average, I0 is the average value of the voltage and current respectively. But here Ericsson used cos, so don't get confused. The Fourier series actually can be represented in many ways. One is by using sine, but with a plus phi n. But if you use a cos, it has to be minus phi over n. Okay, so they are the same Fourier series, but in different representation. You can also find the Fourier series in terms of e to the power of something. Yeah? All right. Okay, so don't get confused yourself, but we want to use the Ericsson's notes. So let's assume that it is represented by Vn cos n omega t minus Vn, and the current here is represented by In cos n omega t minus Vn. Okay, so those are the instantaneous voltage and current for the circuit here. Okay, so therefore the energy is, of course, the instantaneous voltage multiplied by the instantaneous current, and the integral of both voltage and current. Okay, so that gives you the energy transmitted to the load over one cycle, and then you can now calculate the average power to the load, whereby the average power is always defined by the energy throughout the one cycle divided by the period, the time taken for one cycle. So therefore the average power, the actual average power equation equals to 1 over t, and the integration from 0 to t of the voltage and the current. So this is the actual power equation. And if you substitute the Fourier series for voltage and current, we are going to get that equation number 4 here, where average power equals to 1 over t of the integral 0 to t, whereby we have a voltage equation represented by the Fourier series here, and the current Fourier series represented in Fourier series, Vn cos, and we have In cos. Right, so if you solve this, it will come out of the integral of 0 to t of Vn cos omega t of and Im. To differentiate between the harmonics of voltage and the harmonics of current, we use with the m terms for the current and for the voltage. So if this integral, the product of this integral, okay, if you integrate this product, you may get 0 in the case of the harmonics for voltage is not equal to the number of harmonics of current, but it will equal to Vn In over 2 cos Pn minus theta n if n equals to m, which means this integral only exists if the number of harmonics for voltage and currents are the same. Okay, so the final equation, which is equation number 6 here, the average power for any system, for any waveforms, for any system, is always represented by this equation, which is V0 I0, the average of voltage, the average of current if there are exist, plus this the summation of the harmonics, the voltage and current at the same harmonics only. Okay, so if your voltage and current are at the same harmonics or at the same frequency, they will contribute to the voltage, they contribute to the average power. So if you go back to the first waveform that we look at just now, which is a sinusoidal voltage and a sinusoidal current, so the only contribution from that waveform, from that system, is only V1 and I1. V1, I1. So this is the peak value. This is the peak value V1, I1, and the cost between voltage and current, divided by 2. So it comes back to the original equation that we known before. We have known before. So this example, I hope you can go through further more details on this example. This is the case if we have the voltage. This is your voltage, let's say it's a 50 Hertz voltage, and the current is with 150 Hertz frequency. Look at that, there are 3 cycles of current in one voltage cycle. So therefore, if you look at the V multiplied by I and look at the average power will be 0, because the voltage components consist of only fundamental, and the current harmonics consists only the harmonics at third harmonics, the 150 Hertz. So if you multiply both, if you refer to this equation, there are no similar voltage and current harmonics at the same frequency. So that's why there is no average power that is delivered to the average voltage, average power that be delivered to the load. However, in this case, we have the same voltage and current appear to be in phase. So therefore, the voltage is the power is actually V big I big divided by 2, because cos is 0, isn't it? Cos angle is cos 0 is 1, so the average power is 0.5 divided by 2, 0.5. So this is 2 examples, and let's look at another examples here, whereby, okay, so in this case, right, let's look at this example. You are given this is a voltage Fourier series equation. You are given the first harmonics. Remember, Erickson used cos. In our class, we always use the sine, so they get yourself confused. So let's look at this sample here. So the voltage is represented 1.2 for the fundamental, 0.33 cos 3 omega t, which is at third harmonics, and you have 0.2 cos 5 omega t, which is at fifth harmonics. So the amplitude for the fifth harmonic is 0.2, the third is 0.33 for the voltage. And for the current, you are given in terms of 0.6, which is the fundamental, and you have a 30 degree angle, and we have 0.1 fifth. So the current is given by the fundamental of 0.6 with the angle of plus 30 degree. The fifth components 0.1 with a 45 degree, and the seventh components with a 0.1 amplitude and 60 degree angle. So notice here there is no third harmonics. Okay, so therefore, if you compare between the voltage and current here, the power only contributed by the fundamental component, the first components, and the fifth components, because the voltage and current only consist of fundamental and the fifth harmonics. So the third harmonics and the seventh harmonics from the voltage and current respectively do not contribute to the average power. So the calculations of the power, the average power, is given by the amplitude of the fundamental.